Okay, so this chapter uh, talk about the derivation of Bernoulli's equation, and also we'll show you what is the application of Bernoulli's equation in real engineering field. Okay, so I think in the last class we start the derivation, but we don't able to finish it. So let's go back to the derivation. Those are the assumption. Okay, main assumption, we'll consider a cylindrical fluid element is flowing along a streamline, right? Then other assumption, flow is steady, incompressible, irrotational, no friction or no viscosity of the fluid, no heat transfer to the fluid, no heat taking out from the fluid. There is no additional shaft work to the fluid or by the fluid. Those are the assumptions. Now, we'll derive the Bernoulli's equation using Newton's second law. That means you are applying your knowledge of engineering mechanics. So in the figure, you see is two-dimensional flow. Vertical axis is Z, horizontal axis is Y. And there is a streamline it showing from left corner to the upward right. So that streamline, what is the streamline? Every point you make a tangent that will give you the direction of the velocity, right? That is showing over here the vector. This is the S. This at this point, this is the direction of the velocity, and this is the normal vector to the streamline. Now, we took a cylindrical fluid element that is moving from left to right. So why a fluid moving left to right? Obviously, somebody pushing from the left side, right? But at the front have some other fluid. So if pressure on both sides of fluid element is the same, it will not able to move. So in the left side, pressure has to be higher than right side, then it start to move. So what do you consider that area cross-sectional of the cylindrical fluid element is dA. That one very small area we consider. This dA, if you multiply the pressure, then this mass force will work in the left side. That is showing right over here. Because we will apply second law, Newton's second law, we have to figure out the summation of force. Similarly, in the right side, we know fluid is moving to our right. So right side pressure has to be less than the P, right? So you can say pressure is P minus dP, right? But to make easier to derive the formula, we will assume this side is pressure higher, P plus dP. Now, this value of dP might be coming negative. That means this side pressure is low. Okay, so for simplification, we can consider that pressure on the right side is P plus dP. So how much will be the force on the right side? Pressure into dA. That is showing right over here. P plus dP into dA. Okay. Now, you have to think how many force is working there. 2N working the pressure force, and also there is a weight of the fluid. It should work vertically. So weight of the fluid is W. Now, how will figure out the weight of the fluid? If you know volume of the fluid, multiply by rho. That means you are getting the mass. Multiply by G, you are getting the weight of the fluid. Now, how will figure out the volume of the fluid? You see, length of the fluid element is ds. So length into cross-sectional area, that will give you the volume of the fluid element. Then you multiply by rho, then G. This will be value of W. Now, this W working vertically downward, but all the force is working parallel or tangent to the streamline. So we need to divide the W into two components. On if this angle is theta, what is this line? This line is perpendicular to the streamline. So this is 90 and W working downward. We are thinking this angle is theta. So the W we can consider two components. One component along this direction, other component along this direction. So this direction value will be W into cos theta, and this will be W into sin theta. So you see along streamline, now three force is working. This one working downward, opposite of the motion. This one working toward the motion. W sin theta also opposite of the motion. And we are working with moving fluid with velocity. It has a velocity. So you cannot say summation of force 0, but we can say summation of force will be equal to mass of the fluid element into acceleration. Mass of the fluid element you can easily figure out. Volume into rho. What is the volume? ds into dA. This is the volume into rho. They equal the mass. Summation of force, fluid moving along this direction. So you have to take summation of force along direction of the motion. So P dA minus this term equal to this one, right? Now, last class I asked question. So this way, the force working along streamline will be balanced. Now, who will balance this force? That's I was asking. This force working perpendicular to the streamline. So if someone is not balancing, then what will happen? This fluid element will go this direction, it will move. Okay, that means pressure force working along this direction, this W cos theta working this direction, that means it will go somewhere along this direction. But somebody is balancing. So who's that force? That force is the buoyant force working this surface of the fluid element. So they are balancing this W cos theta. But we are not concerned about this force because we are only thinking the force working along the streamline. Okay. So let's see how we can apply the Newton's second law. F is equal to ma. And one more thing, you see the A is the acceleration of the fluid. So acceleration equal to, we know, dv by dt, change of velocity divided by change of time. Now this v, velocity of this cylindrical fluid element, is function of distance travel along the streamline. So I am saying that is s and also time. So v is function of s and t. Now that means we can now figure out dv. dv equal to how much? We can say dv by ds into ds plus dv by dt into dt. We can say that one. Now, in both sides, you divide by dt, then this dt will be out. So you are getting dv by dt, and right over here you will get dt. Now you see this dv by dt is a local acceleration, but this is not, we in the assumption we think this is the steady flow. So this will be 0, and this ds by dt equal to distance divided by time equal to v. So ultimately we are getting dv by dt, dv by dt equal to v into ds by dt. Okay. So let's see, we'll show you again in the next slide, so it will be clear to you. Before that, we show something, that there is some relationship, how we got this angle. Because this fluid element moving along this direction. So if I make a triangle right over here, then what is the horizontal distance? This distance from here to here, obviously dx, and distance from here to here, dz. That will show. This is dx and this is dz right over here. And along streamline, he travel distance ds. So this is the ds. Now, how this angle coming theta? This one is theta. Okay, that I try to explain it in the figure of next. Hold on 1 second. Seems like my mouse is not working. Okay, so this free body, I just show you that how we got this angle. This angle is theta, right? So this line represent our streamline, this one. So this angle is 90, then this one. So this angle is 90, but weight working downward. So this is the weight working downward. So this angle is theta, and this 90. So how much will be this angle? Obviously, this angle will be 90 minus theta, right? Say this angle theta 1. So this angle, this theta 1 plus this angle and this angle, summation will be how much? Obviously 90, because this is 90, this angle. So other two angle has to be 90. So this one is theta 1, this one is 90 minus theta equal to 90. So 90 will be out. That means theta 1 equal to theta. Just simple thing. So this angle is theta. So you need to remember this one. Now we'll apply the Newton's second law along this direction. And what is the purpose over here? This value of dx, dz, we can correlate with this value ds by applying sine theta, cos theta. Okay, that is the intention. And right over here, you can skip this one, but I just show you the formula. You see, f is a function. It is a function of x, y, z, and t. How we figure out the df? df equal to del f by del x into dx, del f by del y into dy. Similarly, velocity of the fluid particle to be a function of s and t. So v equal to function of s and t. And we match with this formula. We like to figure out change of velocity equal to delta f by delta s into ds, delta v by dt into dt. Okay. Now our derivation start from here. The velocity of a fluid particle to be a function of s and t. And now you have this equation we already show you in the previous slide, right? Now this equation, both sides you divide by dt. So left side you are getting this one, right side this one, and this one. So in steady flow, this t will be 0, dv by dt, because this is local velocity. So this equal to 0. So v is coming like s, v equal to function of s now. Okay. So what is dv by dt? Actually, acceleration. So acceleration equal to dv by dt equal to this value we are getting from here. Now ds by dt is the velocity. So we are getting this one. Now there is only single derivative. So instead of del, we can say s equal to v into dv by ds. We can say this one. Okay. Now we'll apply the Newton's second law. And right over here, we just show you that how we can figure out the force and you can figure out the volume. I already explained it. Now we are making force balance. So along streamline, left side working P into dA, positive P into dA. This force P into dP into dA is working downward, opposite of streamline. So negative sign, this term. And W sine theta working along opposite direction of the motion. This is W sine theta, this is W cos theta. So minus, we are getting right over here W sine theta equal to MA. So this is M. What is the AS? AS, we just derive it in the previous slide, right? This is our AS. AS equal to V into DS. That we put over here. Okay. Now this equation will simplify. dV by ds, you see sine theta, this sine theta will take it out. If you apply right over here, sine theta will be how much? Perpendicular divided by ds, right? dz by ds. And this w equal to volume into rho into g. So what is the volume? Area into length. That means this is the volume. Multiply by g, multiply by rho. So if we look in the next slide, right over here, we again mention the what is the m equal to rho into volume. So our rho is the density, volume is dA into ds. That will be, you see, this is the mass on the right side of the equation. This is the m equal to this mass, v into ds. In the left side, you see this p into dA, this p into dA will be out. You have minus dp into dA into w. So w equal to mg. So what is mg? Volume into rho into g. So this is the volume dA into ds multiplied by rho g. So you see right over here, this is our w. And this sine theta equal to dz by ds. That we put it over here. Now you see everywhere is dA. So dA will be cancel out. This will be cancel out. This cancel out. This dA will be cancel out. Then the ds out. This ds out. So dp minus rho g dz equal to v into dv into rho over here. So if we go in the next slide, you see we'll do the integration and we derive the formula. Let's see. So after simplification, we are getting this line. Now both sides you divide by rho. So you're getting dp by rho, and all of them you bring in on side. So you are getting right over here, it divide by rho, then there should not be this rho with the v. So dp by rho v dp. Right over here, into this rho will be out g dz, dividing each term by rho. Now we do the integration. So after integration, you get 1 by rho dp v dp g dz equal to constant. So after integration, for this term you are getting p by rho. This term b square by 2, and for this term g into z. Okay. Now if you both side again you divide by g, then what we getting the over here? P by rho g. P by rho g equal to gamma. So we put gamma b square by 2g plus z equal to constant. So this equation is known as Bernoulli's equation. What does that mean? That means if you apply between 2 points of a fluid system, you get for point 1 this one equal to for point 2 this one. That means this value summation of these three is always constant. And these three, this term, first term, P1 by gamma is called pressure head or pressure energy. This one is called velocity head or kinetic energy. This one is called potential head. But summation of these three will be always same. Okay. Any question? Any question? No? Okay. You see the three component of Bernoulli's equation, we explain it right over here. P by gamma, this is called static pressure head or pressure energy per unit weight of the fluid. And V square by 2G, kinetic head or kinetic energy per unit weight of fluid. And Z, potential head or potential energy per unit weight of the fluid. Okay. Now, this equation you can represent different way. This is our Bernoulli's equation. If you both side you multiply by gamma, then this will be only P. This will be gamma equal to rho G. This rho will G will be out. So rho B square by 2G. This will be rho dz equal to constant. Now, if you look carefully this equation, could you hold on 1 second? Okay. What will be unit of P? Unit of B square by 2G in unit of rho G Z. Anyone? Anyone could tell me? Hello? Okay. I'm not sure you are there, but P is the static pressure, unit of pressure. Equation, how did you know equation is wrong or right? There is a one thing that unit of the all the term has to be same. This equation has three parts, right? Like P, then summation rho B square by 2, then rho G Z. Unit of the each term has to be same. If it is not same, that means equation is wrong. So you see is the P is the pressure. This pressure. So B square by middle term, I'll say this is also a pressure and it has to be same. Rho Ga also is pressure. That means P is called static pressure of the fluid or actual thermodynamic pressure of the fluid. And rho V square by 2G is called dynamic pressure of the fluid. And rho Gz is called hydrostatic pressure of the fluid. Okay. Now, actually, what is the application of the Bernoulli's equation? For What does it actually mean? That means fluid has a three energy. Number one, it has an energy P by gamma. Second energy, it has V square by 2G. Third energy is Z, that is potential energy. This value is always constant, these three. Now, what is the application? For example, you are working in a company, they build the pipeline to transmit the petroleum. Okay, so your pipeline might go through under a river or might go through top of a hill. It's going like that. Okay, I'm sorry. Let me draw it again. So your pipeline is going this way. Okay. Now you are applying Bernoulli's equation in several points right over here. So what is the P? You measure the pressure at this point. You measure the velocity. Now what is the Z? Z is the potential height. What is the potential energy? MGH. Say you are in a roof of a building, you are sitting right over here, then how much energy you have with respect to the ground? You are just sitting, right? If you jump, your bone, everything will be crushed. Who will do the crush? Your energy, because you have stored energy, mgh. So depends on the height. So you have only one energy, mgh, that is called potential energy. Now, you running in the rooftop, then how much energy you have? You running in the rooftop, that mean you have kinetic energy, plus you have potential energy. These three are two energy you have, you running. Now, instead a human body, we are thinking a cylinder full with gas, and that one is running in the rooftop. Then what will be happen? He has one more energy. Respect to the ground, he has potential energy that depends on the height of the building. Then he has kinetic energy because it is moving. So depend on the velocity, the kinetic energy will be depend on the velocity. If velocity is high, kinetic energy will be high. So potential energy depends on the height of the building. Now he has one more energy, that inside the cylinder you have some fluid and it has a pressure. So you have pressure energy. So total three energy remain inside the system. So a pipeline right over here, this point, if I think this is my reference line. So I applying Bernoulli's equation right over here. I'm saying this is 0.1. Then what will be the energy right over here? P1 by gamma V1 square by 2G plus Z1. Z1 mean height from your reference line. If this is reference, it say this is Z1. Now you're taking right over here. What is your Z? If this is 2, how much will be Z2? Very few, right? Then this will be equal to P2 by gamma. You can say this equal to P2 by gamma plus, let me erase some of this equation. Okay, so you have then V1, V2 square by 2G plus Z2, right? And you apply right over here, then you say P3 by gamma plus B3 square by 2G plus Z2 equal to 0. Okay, so all three in left side is coming 100. Then how much will be this one? Obviously, this one summation has to be 100. Okay, so right side, this will be 100. What is the beauty of this equation? If right over here, you know the height, you know the velocity, you know the pressure, then you can figure out the, say right over here, you know the pressure, you like to know the velocity of the fluid, you can easily figure out. That means by applying this Bernoulli's equation, it relates pressure, velocity, and the datum head or potential head of the fluid. There is a uh, other term they use to describe this Bernoulli's equation. Is called pressure head, velocity head, and datum head. Summation of all three, pressure head, velocity head, and datum head, is equal to constant. That they describe the other way. Okay. So in the exam, you will have question something that derive the Bernoulli's equation, or I'll give you the equation. I say derive this equation with all the assumption. Now, you see what is the application? You see this is the pipeline is showing took from the website. There's some company, they are supplying uh, oil through pipeline, and now we see the pipeline is going under the hill, sometime top of the hill. You see elevation is not the same. Now this point, you know, for example, right over here, you know the pressure, you know the velocity, you know the datum head. Then how much will be velocity right over here? How will figure out? If you know this point, if you know the pressure, this point say you know everything. This point you know the value. If I say this is 0.1, this is 0.2. So this point, you know, you have a pressure gauge or right there, you know the P1, you know the velocity, you know the Z1, and right there, you know the elevation. That means Z2, you know. V2, you don't know. You need to, you like to figure out. But pressure, you know. So V2, you like to know. If all these five value you know, you applying Bernoulli's equation, you can figure out the V2. Okay. So, and also, alternatively, if you know the pressure, you know the velocity, then you can figure out the pressure. So actually, if some point, say you look right over here in the upper pipeline, right over here, something is going down of the hill. So what will be happen there? When is coming down the hill, fluid velocity will increase. But after getting bottom of the hill, then he need to climb, right? Velocity will be little bit reduced. If velocity reduce, then what will be happen? Say, or for example, through a pipeline, water is coming. So right this point, you apply Bernoulli's equation. So you get P by gamma. You get B square by 2G, and you get that of head. Say P by gamma is coming, I'm saying 70. You got 70. B square by 2G, you got 20. Z, you got 10. How much the summation? Total is 100, right? Now, fluid coming over here, you close the bulb, then what will be happen? What will the summation of total energy right over here as per Bernoulli's equation will be how much? Still, it will be 100. But you close the gate, what will be the velocity? Velocity 0. Now, right over here, all three summation is 100. As per Bernoulli's equation, here has to be 100. But here we have only two terms, is P by gamma plus Z. Because V already 0, because you close it, the bulb. Now, these two, as per Bernoulli's equation, has to be 100. How is it possible? Your Z almost same because it's horizontal line. So how much will be the pressure then? It will be same or it will increase. You see, Z is 10. So this is 10. Now to make 100, this value has to be how much? This value has to be 90. So you see, pressure energy at point 1 was 70. At point 2, it become 90. Because always total energy has to be 100. So if you close the valve, still fluid is coming, then what will happen? Due to the pressure, your pipeline might be burst. So if you work in a petroleum company, you need to check the elevation of all the points. Say right over here, how much, right over here, right over here, how much. Then you need to check the which point is critical. Where is velocity going too high? Where is velocity is decreasing? Where is pressure increasing? Now, a lot of company, they use helicopter, say your pipeline from Canada to the Alaska or Canada to Texas or from Iran to Afghanistan through Pakistan through China. And how you going to supervise this pipeline? You have option, you have use a helicopter and flow over the pipeline and check the pipeline, right? This is one option. Now, if you're somebody visiting your company and he like to check that which point is the critical point, which point is possibility to get bust, how you can figure out, how you can show him. One option you have, if there is a road, you can drive with him around the pipeline from say Iran to China, one option. Other option, use a helicopter and fly over the pipeline and show him the critical point, right? But both is not easy due to the weather, again, time, right? So you have to figure out a alternative way. How? If you make a graph, say this is my starting point at Iran, and this is the distance from Iran to say Pakistan, Lahore. I'm putting Lahore. And this is my distance x. Along top line, vertical direction, I make summation of total energy. So it's say P1 by gamma, V1 square by 2G and Z1. Okay. Now, you plot only Z1. How much the Z1 in Iran? Tehran, you say 0. How much at the border of Iran? Z1 is this much. Right over here, Z1 this much. You coming over here, Z1 this much. Then you make a line. Say is going this way, then going. So if someone visit, you just show him the graph. Say, this is my elevation pattern of my pipeline. Now, similarly, you can plot the V1 square by 2G. So say at the Tehran, it is right over here. Over here is constant, then over here is low, then again increasing. Then you make a line. Okay. Similarly, you can make this line, P1 by gamma. You saw P by gamma, say right over here is too high, then it is again increasing, then again decreasing, and just show him the graph. So he can observe that what is the pattern of your pipeline from one region to other region, where is pressure is too high, where is velocity is too high, where is data phase is extremely high or extremely low. Okay, so this is the application. So let's see in the actual cases what type of the line they are used. So you see in Bernoulli's equation that this term equal to constant. If just rearrange the equation, then V square rho into V square by 2G. This is called dynamic pressure, and this is called hydrostatic pressure, rho G Z. So if you make summation of this one and this one, that is called pressure line. And if you summation all three, that is called energy line. And you see P and rho G Z, that is coming related to the pressure, that is called a hydraulic gradient line. So let's show you our hydraulic grade line. So there is a two line. Number one thing, HGL is called hydraulic grade line. It represents summation of P by gamma and Z. Or you can say P plus rho G Z, same thing. This line is called hydraulic grade line. So you see in Bernoulli's equation, we have P by gamma B square by 2G plus Z. So only these two terms we are taking, P by gamma and Z. Then at different point, you make a line. So that line is in the bottom, dotted line. That line is called hydraulic grade line, the bottom one. But B square by 2G, we didn't add that one, right? Then you put B square by 2G, that will be this line. So this line is called energy grade line. That means this line actually represents the all three. First you put P by gamma plus Z, you'll get one line, this line. the bottom one with dotted line. Then summation of all three, you get this line. So how did we see? The bottom one is summation of pressure and the potential energy, P by gamma plus Z. And this one, all three, that means the difference, this much distance is represent the kinetic energy of the fluid. Okay. Any question? No? Okay. So I feel all of you is doing great and you are understanding. Okay. Now energy grid line. The line that represent total head of the fluid. That means is a total energy in the Bernoulli's equation is called energy grid line or energy line. The difference of height, energy grid line and hydraulic grid line is equal to dynamic head. Bernoulli's equation we can describe into this is pressure head, this is velocity head, and this is potential head. Sometimes you go for job interview, they ask what is Bernoulli's equation. Then you can write down P by gamma B square by 2G plus Z equal to 0. And they ask you what is P by gamma, what is B square by 2G. Now P by gamma, if you don't know, you might say, sir, this is pressure divided by the specific weight, right? But you cannot say like that. You have to say this is pressure head. Sometimes and you say this is velocity head, this is potential head. And sometimes they ask question, could you tell me the Bernoulli's equation in one sentence? So you need to say the summation of pressure head, velocity head, and potential head is always constant. That you have to say. Okay. So you see, look in the graph. This is your total energy line. In the top and bottom, you are getting hydraulic gradient line. Okay. Now, the summation of these three has to be always constant. That means fluid energy is not changing. You are working Dhaka City Corporation and they have a water treatment plant by the river Jamuna. You treat the water, you put say 5 pump, they are pumping the water through the system pipeline. Or they only one pump. It will be enough to reach water in Dhaka city. Or you think the pipeline is building from Iran to China. So only one pump, if I put in Iran, the petroleum will go all the way to China. Is this possible? If it's not possible, then what the reason? It is as per Bernoulli's equation, it is possible because total energy you put say in the river Jamuna, in the pipeline, you have a pump, a bigger size pump, you put total energy P by gamma B square by 2G plus Z 200. So all the way right over here has to be 200, over here 200, over here 200. So if this point has a flow of water, obviously there will be flow as per Bernoulli's equation. If this is true, then one pump will be enough to supply crude oil from Iran to China by pipeline. But it is not possible because Bernoulli's, he didn't add the frictional loss in the pipe. Okay, so when you supplying the crude oil or water, there will be, due to the friction with the inner surface of the pipe and the fluid, some energy will be lost. That's why it should not come. What need to do, in multiple point, you need to add some pump, then water will flow to your destination. Same thing for a pipeline from Iran to China, you need to have multiple pump in multiple location. Okay, so you see the ideal energy line is a straight line with blue color. It's the ideal line, but in reality the curve will be like that, and this much loss is actually due to the friction. Okay, so what we need to learn from here, what is energy grade line or energy line, and you need to know what is hydraulic grade line, HGL. Okay, that you need to know. Okay, so in Bernoulli's equation, you see right over here, if you rearrange this equation, it will have this form. So P is called static pressure. This is called dynamic pressure. This on rho GZ is called hydrostatic pressure. Now, how we can measure that pressure? You can measure the pressure by manometer, right? That we learn in the manometer. By attaching some pressure gauge, you can measure the pressure, right? But you can do some other way. Number one thing, static pressure tap is simply a hole drilled into a wall. That plane of the hole is parallel to the flow direction. It measures the static pressure of the flow. For example, you have a pipeline. If you make a hole at the surface, then if through the hole there is two things work. Fluid pressure will work upward, right, through the toward the hole. Atmospheric pressure work downward. If the magnitude of these two pressure is same, then there will be no leakage of water or fluid from this hole. But if inside pressure is higher than the atmospheric pressure, then fluid will come out through the hole. Okay, this way you can measure the static pressure of the fluid. Other thing, that you can use a pitot tube. If you use pitot tube, from the pitot tube you can measure the pressure and also you can measure the velocity. And this pitot tube, application of pitot tube is very important in your lab. So what is pitot tube? It is a hollow tube that placed longitudinally in a direction of the fluid flow, allowing the fluid flow brought into rest. That means you stop the flow. Then where velocity approaches, it is used to measure flow velocity and stagnation pressure of the flow. And we'll show you how it is work. For example, it is kind of L-shaped tube, L-shaped tube, and there is a little hole over here. So when fluid is flowing, then hitting right over here, not at the hole, the fluid will be stopped, velocity will be stopped. If velocity is stopped, then that velocity, kinetic energy of the fluid will be converted into pressure energy. So that means, you have two pressure. One is static pressure P by gamma. Then V square by 2G is called dynamic pressure. But you stop the fluid right over here. So this energy will convert into pressure energy and then make summation with this one. That means it will increase the fluid pressure. That is called stagnation pressure. For example, you have a river dam. Now, say river dam like that, and this side, water height is gradually increasing. Say water coming through the canal, and you stop it. Why water is rising, going upward direction? What is the reason? Because you stop the flow by making the dam. That means you bring the velocity zero. Stop it. So where is going that kinetic energy? It converted into pressure energy. That's why gradually rise the height. And if your dam is weak, then what will happen? It will break down, right? Same thing. A cricket ball, somebody batting, you are fielding, coming with the high velocity, and you just holding your head strongly, firmly, then what will happen? You get hit in your hand, you got pain, right? But you gradually hold it, you know, by little bit coming down motion. That means gradually you make the energy zero. You'll not feel any pain in the hand. But if you just strongly try to hold it by making your hand more stiff, then what will happen? Then it will hit your hand with, and you will get pain. What is the reason? You get pain because the kinetic energy of the ball will be immediately zero. You're making it zero by holding your hand, making extremely stiff. Then that kinetic energy will be converted into pressure energy and you'll feel pain. But gradually you reduce the velocity. That means when you hold the ball, you little bit you keep the hand in downward motion. That means you making the velocity zero, not at 0 second. That means you're giving some time, gradually reducing the kinetic energy. So same thing in the fluid. In any region, you stop the fluid flow, then there will be increase of pressure. Okay, that pressure, how much pressure is increasing, that we can measure in the pitot tube. And not only pressure, by using pitot tube, you also able to measure the velocity of the fluid. Then other thing, piezometer. What is piezometer? I think we already show you piezometer in the manometry class, right? So right over here we say what is the piezometer. This is the say you have a pipeline. You attach a tube with the pipeline. Then the fluid try to go upward direction, atmospheric pressure try to put him down. So by measuring this height and manometer, you can figure out the pressure inside the tank. Similarly, you have a inclined pipeline, you have piezometer right over here, and you can figure out the measure the pressure of the fluid. Now, but how will measure the pressure in the by using pitot tube? This is the configuration of the pitot tube. And in our lab, if you see the wind tunnel, they have used the pitot tube. And how it is work? Say you put this one in a pipeline or in a flow, in a, say, this is way air is coming with certain velocity. Air is coming along this direction. Then what will be happen? Air coming right this through the point, it will flow, but right over here coming, it will stop. It cannot, velocity will be 0. Air hitting the right over here, he cannot flow, it will be stop, right? So there will be pressure will be increase in the fluid. So if you attached a so you see pressure fluid right over here, the fluid coming right over here, the velocity will be 0 right over here. Because due to the 90-degree angle, fluid need to change the direction, right? So if we attach through hole a tube, and through this tube we attached a hole, and you will see there is a manometric pressure difference. From that pressure difference, you can measure the velocity. Also, you can measure the stagnation pressure of the fluid. Let's see how we can I just give you the preliminary idea. Then we can show you how we can figure out by using a Bernoulli's equation, how I apply that equation in the pitot tube. So right over here, you see is a pitot tube. Okay. So fluid is flowing. Right over here, it's a velocity will be 0. And there is a one more hole in the pipeline. Now, if you attached a tube, U-tube manometer, then what will be happen? Right over here, velocity is 0. Right over here is not 0. So right over here, you have pressure P by gamma, static pressure, because velocity is not 0. The fluid moving along this direction with kinetic energy, V square by 2G. But fluid right over here, he has two components, P by gamma plus V square by 2G. By these two energy, fluid is coming from this point to this point. When it's coming here, then velocity, you are stopping. So this mass energy converted into pressure energy. So converted pressure energy and this P by gamma, they got together and increase the pressure. So if you increase the pressure, if you add the manometry, then what will be happen? This side will be higher pressure, this side will be low pressure, and this manometric height will be sense. And from the deflection of the manometric height, that means this mass distance between right over here and right over here, this is the age. From this deflection, you can measure the velocity of the flow, and also you can measure the stagnation pressure. Okay. Any question so far? No question? Okay. So what is the stagnation pressure? Sometime we put short question in the exam. It's saying sum of static, dynamic, and hydrostatic pressure is called total pressure of the fluid. Bernoulli's equation states that total pressure along a streamline is always constant. Sum of static and dynamic pressure is called stagnation pressure. Expressed like that: P stagnation equal to static pressure plus kinetic pressure. Stagnation pressure represents the pressure at a point where fluid brought to a complete stop isentropically. Okay, isentropically means entropy constant. Now, we know this is P stagnation pressure. Okay, you see there is a piezometer and there is a pitot tube, kind of L-shaped tube put in the flow. So what will happen? Due to the pressure at the, you look at the piezometer, at the top of the piezometer working atmospheric pressure, right? You try to push the fluid down, and fluid is flowing with how many energy? 3 energy. P by gamma, flowing with P by gamma, then B square by 2G, then Z. And you see this is horizontal. So if you take point 1 and point 2, both cases Z will be same, right? So you see fluid moving along this direction, right over what happened? Fluid still moving. So due to this pressure component, fluid try to get out from this piezometer, try to move upward direction. But atmospheric pressure pushing him down. If inside pressure is higher than atmospheric pressure, then height of the fluid is increased. So that's why you see a little bit deflection right in the fluid element, the mass deflection. Okay. Now, but when fluid coming right over here, coming with how many energy? With this 2 energy, P by gamma, this 2. Okay. But you stop the velocity, then this velocity is increased. Is converted into pressure energy. That's why total pressure is increasing than in piezometer. So that's why in the top, in this pitot tube, in the top still working atmospheric pressure. And right over here, you reduce the velocity to 0. So kinetic energy of the fluid converted into pressure energy. That converted pressure energy add with static pressure P by gamma, and it increase the pressure more. So through this pitot tube, fluid is try to move upward due to the pressure. But this pressure is extremely high and higher than the atmospheric pressure. That's why fluid move upward this much height. Okay. Now, if I apply the Bernoulli's equation at point 2, we are saying at point 1, velocity of the fluid is V, and Z on Z2 is same, both point. And at point 1, pressure is P, and point 2, velocity is 0, because you stop the flow right over here. Right over here, your velocity of the fluid is 0. And P2, pressure at P will be higher, right? Because you make the velocity 0, kinetic energy converted into pressure energy. So that pressure, as per definition, is called stagnation pressure. So P2 equal to P stagnation pressure. Now you apply Bernoulli's equation both sides. Then what you will get? P1 by gamma. So P1 by gamma plus you say V1 square by 2G plus you will say Z1 equal to P2 by gamma plus V2 square by 2G plus Z2, right? Now, you see Z2 in both case is same. So your Z2 will be out. So you will get this Z2 and Z1 will be out. V2, you make it 0. So V2 will be out. So finally, what are we getting? Left side, you are getting P1 divided by gamma plus V1 square divided by 2G equal to P2 by gamma is right side, right? This P2 by gamma, P2 is called stagnation pressure because this point velocity 0. And velocity 0, you make it forcefully. So this will call stagnation pressure. So by rearranging this equation, you can figure out the V1 from here. How? You can say V1 square by 2G equal to PS minus P1 divided by gamma. Then you figure out the V1. V1 equal to, you get this one, 2 into P stagnation minus P divided by rho. Because this gamma equal to rho G, then G will be out. So you see, if you know the stagnation pressure of the fluid, and if you know the pressure at point 1, easily you can measure the velocity of the flow, V. Okay. Now let's see how you can, if you look a simple way, and if we apply the manometry, then you can see easily we can measure the velocity without measuring the P stagnation pressure. Because you, this piezometer, if you, with these 2 points, if you add a manometer, E2 manometer, then what will be happen? Right over, say, you put manometric fluid, right? If pressure is same, both will be along this point, right? But pressure in the right side is more, then what will happen? He'll try to push up, and this will be pushed down. This will become this much. So what is the difference of height? Difference of height, you are getting this much, right? So if you know this difference of height, then you can figure out, measure the velocity without measuring the P stagnation, without measuring this pressure at point 1. Okay. And we'll see that how we can figure out the velocity of the fluid by measuring only deflection in the manometer. Okay. Right over here, we just rearrange the same figure we use, but we choose to height. For example, we choose this height. We choose this height. Okay. This height is same. Then we choose this height. Okay. Then we apply manometer. So if you look the figure in the next slide, right over here, velocity 0. So we are thinking that distance from this point to this point, vertical height is h, that means difference. And this depth, this point to this is h1, and from surface of the pipeline to point 1 and 2 is h2. Okay. Now we like to figure out the static pressure at point 1. How we can figure out the static pressure? We apply the manometry. You start from right at this point and come to the point 1. Point 1, this point is the same because same elevation. Remember, manometry. Pressure remains same along the same horizontal line. So from here to come down here. So P1 equal to atmospheric pressure, because right over here we have atmospheric pressure, right? Then right over here we put P atmospheric pressure. Then you come down in the bottom direction. How much distance? Your distance is first this one, H1, then coming down by H2. You're coming down positive. So H1 row of the fluid, this fluid, into G, plus H2 row of the fluid into G. So this mass value is the pressure at point P1. Now, how much the pressure at point P2? P2 also called stagnation pressure, that we express by PS. Okay. So instead of P2, we are saying PS. So PS will be how much? That means pressure between 2 point and this point will be the same. So we will coming down from upper point to right over here. So how much the pressure over here? P atmospheric pressure. So P atmospheric pressure this one plus we coming down from here to here. That means H rho G. Okay, manometric fluid. Okay, it's the same fluid. We can say this one also F. So we are coming from here to here. This throw this down H. Then you come down from here to here. Distance H1 rho F G. Then is coming from here to here. H2 rho F G. Now this portion of the fluid, right now you see the same, the H. What is the H? Deflection between 2 points, this point and this point. But if you attach a U-tube and put some other fluid, then this much density will come, density of the manometric fluid. That's why I just put a rho, or I can put, if you put rho F, as per figure, you need to put rho F. But I just put rho, or you can put rho M. Now, you figure out the difference, PS minus P1. Then you see this value will be out. And H1, this one will be out. If you subtract this one, this will be out. So you remain only this one. H rho M G. Okay. Now, if you look, if you apply the Bernoulli's equation between point 1 and 2, then what are you getting? This is your Bernoulli's equation. At V2, V0, Z1, Z2 is same. P2 mean PS. So our equation coming right side, PS by gamma, V1 square by 2G, P1 by gamma. Then use us, and you see this one, we got it from here, H rho G. From here, you figure out V1 square by 2G equal to PS minus P1 divided by gamma. Now, PS minus P1 equal to rho G H, rho G H. And gamma equal to how much? Rho G. So this rho G will be out, only have H. Then you can figure out the V1. V1 equal to root over 2GH. Okay. And right over here, you see in the manometer and the flowing fluid is same. That's why right over here, this density will be out. But if you is not the same, density is not the same, then what will be happen? Then this one will be H rho M. And in the formula, you are getting V1 square by 2G equal to PS minus P1 divided by gamma, right? This gamma, they put rho M. This gamma is the flowing fluid. So this will be equal to PS minus P1 divided by rho F, flowing fluid into G. Okay. Now this G will be out. Now you are getting V1 square divided by 2 equal to PS minus P1. PS minus P1 equal to H rho M into G divided by, you are getting right over here, rho into G, rho into G. And what is this rho? Rho is the flowing fluid, okay, flowing fluid. Then this G will be out. So finally, if I erase that one, finally you are getting V1 square divided by 2G equal to H rho manometer divided by rho of fluid. So your V1 is coming little bit different. That means V1 equal to 2 rho GH into, you have this ratio, rho M divided by rho F, then root over. But if these two fluid is the same, fluid flowing through a pipeline is water. In the manometer, you also put water, then these two will be same. You have only 2G root over 2GH. Okay. Any question? Any question?
Sir, why rho m is used here?
What to say? Why?
Rho m. So rho f is for fluid.
Yeah.
So why?
Rho M. Okay. Rho M. Sometimes what happen? You need to, if pressure in the pipeline or say in a cylinder is very low, then you can use same fluid in the manometer. Say you are checking pressure in a pipeline carrying water. So you can use the water in the manometer. And for you can see easily, that's why you put some color, say add some red color, but density is same. In that case, rho M and rho F is the same. But sometime you say in the pipeline is flowing petroleum oil, very high density. Then you put the water density is lower than the petroleum oil. So you'll not get, you need very high deflection you will get. Might be more than feet, very hard to observe or count. In that case, you will use a fluid heavier than the fluid flowing in the pipeline. Then you can use mercury or any other fluid. You got it?
Yes, sir.
Other thing, say through a pipeline is flowing natural gas. You cannot see, right? So in the mathematic tube, if you don't put any liquid, then how will figure out the deflection? Because gas is invisible. But in that case, you can use water, right? Because
Yes.
deflection of water, you can visible, or you use some color, some dye in the water, or you can use, say, for example, kerosene oil, mustard oil in the manometric fluid. Then your density is not the same. Then you have one extra term, root over 2gh into rho m by rho fluid. Okay?
Okay, sir.
Clear?
Yes, sir.
Okay. Our class is how long?
10:30. Shesh.
10:30, almost finish, right?
Yes, sir.
Okay. Did you join in solid mechanics class? All of you?
Yes, sir.
Okay. Yeah. Join it and encourage your friend to join. I think we have 2 more weeks to start the solid mechanics class. But I have one complaint to all of you that when I ask question that do you understand it, I see no response. I am not sure that you are understand or you are listening the lecture, but I got better response from your A section. When I ask question, at least I see 3-4 student they response. Okay, so what I request, you should not feel shy. If you're not able to ask question in English, you start ask question in Bangla, no problem. Okay, and don't feel shy that why I should not ask question. Any stage you understand or you have confusion that how sir get this line from line 1 to line 2, you should ask question. Okay, so this chapter is very important. Derivation of Bernoulli's equation is very important, and also this equation is valuable in your practical life. You go for work. Okay. Other day I gave a example that you join, for example, in Eastern Refinery, and they build a tank 2 miles away to store the liquid petroleum. And they're saying, okay, design that pipeline and figure out what will be the capacity of the pump to deliver crude oil from Sitagan port to that tank. And you have to figure out the capacity, that it will be 50 horsepower or 20 horsepower. And you will use multiple pump or one pump will be enough. Okay. So this chapter is very important, and I feel you should give more concentration. Okay. And your attendance, I am taking from the Zoom, but I feel a lot of students abusing it. They're just joining in the last moment. Since I am taking the same way, it will continue same way in the last class too. But when you start solid mechanics class, I'll took the attendance differently. Okay. Okay. So any question? No question?
No, sir. No questions.
Okay. Thank you very much, and see you tomorrow. Right? Not tomorrow. We have class
Sir,
will
not
be
tomorrow, sir.
on Wednesday.
Yes, sir. Wednesday.
Okay. Okay. Thank you very much, and stay careful.
Thank you, sir. Assalamu alaikum.